Group of faculty, another who was here last year, Brian Couch, who really helped us catalyze sort of education research on campus there and really build it up to a robust program that it is. And that includes funding from Howard Hughes and other sources to run a series of workshops, and one which I participated in, which was really instrumental in affecting how I did things in the classroom. Marilyne's received many awards. She's currently the recipient of a career award from NSF. And over the last 3 years, Marilyne's been spearheading the use of classroom observation tools, primarily COPUS. And they had a prominent paper published in Science last year where they presented data from a comprehensive use of COPUS across different departments and different institutes. And her talk today will address some of that. So the title is up there: How Science, Technology, or how are Science, Technology, Engineering, and Mathematics taught at North American universities. So I'll turn the floor over to Marilyne. Thank you.
Thank you. Thank you, everyone. So the first thing I'm going to ask you to do is to calm down, because we don't have a microphone. So calm down. If you're sitting alone, you're going to have to find a partner, because we'll do a little bit of reflections and predictions on the data that I'll share with you. So even if you're all the way in the back, I can see you. You can't be by yourself. You got to calm down. Thank you. All right, thank you so much. It's been a pleasure to be here. Thank you so much for the invitation. My husband was like, "You're going in February in Manitoba? Like, what's wrong with you?" And it's actually, well, probably not warmer, but the weather is much more enjoyable here than it is in Nebraska, like right now in the next 24 hours. So I'm like, yeah, he's dealing with freezing rain right now. I'm like, this is sunny, and I have tunnels. It's cool. All right, so as Steve mentioned, today I'm going to give you a brief overview of what my program is about, but focus specifically on two studies that we've conducted that look at instructional practices in STEM classroom in North America. As you will see, we were able to have one institution from Canada, so we could say North America, which was very exciting. So before we start, I want you to think about the following questions and raise your hand if you can answer yes to that questions, okay? Can you describe how science is taught in your classroom? Could you describe it to a peer? Raise your hand if you can describe how you teach your science in your own course. Hopefully everybody can describe what they're doing in their classroom to some extent. Okay, can you describe how your colleagues are teaching in their courses in your department? You should own your answer, okay? And look around as the hands goes up, okay? Can you describe how people within your field at other institutions are teaching? Okay, the number is decreasing. I'm getting a lot more wavy. All right, and then can you describe how people are teaching your science in Canada? Okay, we're down to one maybe. Okay, and so to me that's why I'm doing this research. We actually don't know how we are all teaching science, right? And so I have just an inherent curiosity in knowing how faculty are helping students learn the concept they are teaching in their classroom. So that was, and part of the studies that we are doing will help resolve some of what we are observing here is that lack of knowledge. Why are we focusing on teaching? So there's, beyond that just innate curiosity that we want to know how we are all teaching, what's happening in the classroom at the undergraduate level, especially those first 2 years, is actually critical from a national perspective. So, and I apologize, I'm bringing a very US-centric point of view here. So this is the arguments that we are making in the US. I don't know the extent to which that applies here in Canada, but this is the problems that we are facing in the US and how we are seeing the undergraduate curriculum as a place where we can address those issues. And so one of the priorities in the US is to develop a more literate society where they actually understand science, understand the process of science. And we also have a shortage or perceived shortage of STEM majors. And so we know we have trouble retaining students in STEM majors. And so there's a lot of emphasis of identifying strategy and implementing strategy that helps retain students. And we know from research, so this is talking about leaving. This was a study done in 1997, so quite a long time ago. A very extensive study that looks at why STEM students leave the STEM majors. And this study is being currently repeated, and they're finding the same thing like that many years later. And so what they found is the instructional practice that students experience, especially in the first 2 years, really helps students decide whether or not they're going to stay in STEM. And so, and even for students who stay in STEM, they're saying those practices that they're experiencing in those first 2 years are problematic. And so we know that if we start paying attention at the classroom environment, we can help address some of the problems that we are seeing, retention and education of a more literate citizenry. And so they are, and I think speakers you've had previously in this series and in your PALS group, you probably know that there are a lot of strategies that have been developed to help improve those learning environments. And so you can put them all into this umbrella of active learning. That encompasses a lot of different practices, but the idea, I like this definition that I took from Freeman paper, it's engaging the students in higher order thinking. So sometimes we have a misconception when we say active learning. We have this misconception that it's just about students moving around or being physically active, but it's all about cognitive activity. And so that can happen through group work, but it's not just about talking to your neighbor, it's like the question you're trying to answer as you're talking to your neighbor that we want to focus on. And so this active learning strategy, there's a lot of evidence behind them that support the effectiveness. And so this meta-analysis, if you're not familiar with it, I would advise you to go ahead and read it. It's one of the most comprehensive meta-analysis that we have to date. And it demonstrates that students in traditional lecture courses are about 1.5 times more likely to fail. And their definition of active learning and what they counted as active learning was very, very broad, and it can be as a little thing as a think, pair, share to a much more like cooperative learning structure. But it's unequivocal that having active learning strategy improves students' retention learning, retention in the courses learning, and also attitudes towards the field. So there has been in the US a lot of initiatives to try to promote the use of this strategy, because we've been having those for a long time on hand. There's a National Science Foundation. We have the Association of American Universities. There's all kinds of initiatives to try to promote the use of these strategies. And yet, so this is the National Academies came up with a report to try to understand the status and thinking about metrics that could be used to monitor our progress with how we are teaching STEM courses at the undergraduate level. And this report was just published in 2018. And what they found is that we actually don't really know how much impact all these big initiatives have had. So we don't, like the answer to the questions at the beginning of the slides kind of exemplify our level of understanding of how much this initiative has impacted instructional practices. And so my argument is that for these initiatives to be successful, we have to focus on the faculty and understand the faculty better, right? And so we have to think about how faculty are thinking about their teaching and what they are doing in the classroom. And so that's how I see we can kind of make sure that all these change initiatives that we are developing could be impactful if we actually understand our faculty better. And so my vision so in discipline-based education research, which is like people like me who do educational research but are sitting in science departments, traditionally we've been focused on the students in the classroom, how do they learn, and then developing those active learning strategy and demonstrate that they improve students' learning. And so my argument is that that's good, now we have those, now we need to shift our focus to the front of the classroom and study the faculty and understand how they're functioning, what they are doing, so that we can help them adopt those new instructional practices and identify a strategy that make it that make it easy for faculty to adopt these strategies. And so in my lab, this is pretty much what my lab does in one picture. So let me orient it to this. So we have the discipline-based education researchers, people like me. We have, over the years, produced all kinds of different products, like instructional material, assessment tools. You had Brian Couch who came give you an idea of multiple true-false. So we have a lot of products. We disseminate those products to the faculty. We're hoping that they adopt it, and then the faculty are the one in charge and can shape the classroom, right? And so my goal is to make sure that this is happening. And my argument is in order for this process to take place, we have to understand best ways to disseminate information. So traditionally, we've been doing it through workshops or just publishing results of our studies. Is that effective? In what ways can we improve those strategies? We have to study like what happens when faculty become aware of these practices. What does it take for them to incorporate them into their practices? How can we help them do that? And then once they choose to adopt, many studies will show that they really adapt. And so we have to understand what do they do to the practice that we teach them, and how do they actually, what decisions go through their mind and when they try to implement it in the classroom. So how do they make adaptation? Why do they make those adaptations? And then finally, we have to understand what actually takes place in the classroom. So in my group, we're studying all these various things, but today I'll focus more on like what's happening in the classroom and report on 2 studies where we focused on this. And so those are the 2 studies. And the research question that we were trying to address was what are the different instructional styles that STEM faculty implement in undergraduate courses. So I made an assumption that there was only a couple of styles that were used across instructors in STEM field. And then how do these styles vary by STEM discipline, type of course, class size, and classroom physical layout? Those are all answers that we didn't know. Even if there was observational or some study done, usually they were done within a specific discipline. So we did a study that allows us to compare across discipline. All right, so how do you measure teaching? I just had an argument with my graduate students the other day. She was like, oh, she was talking about good teaching, and we should value good teaching. And I'm like, yeah, how do you know what good teaching is? It's a very hard question to answer. And so we have our wonderful students' evaluations that's traditionally been used as a way to measure teaching. Opinion varies, but in general, it's like they're not very good. They're very biased. There's a lot of issues with them. That tells us good information about students' experience in the course, but not really anything about teaching effectiveness, right? And so it's valuable from that perspective. We want to know what they feel, how do they feel about the course, but we should not use that as a way to say this course was taught effectively. Then there is, in DBER, we have developed a lot of self-report survey where we ask faculty, how do you teach, essentially? Those are prone, depending on how they are used, they can be prone to validity issues. And so we've seen that if these surveys are used in the context of evaluating, evaluating professional development workshops, faculty have a tendency to be more positive on the evaluations because they want the workshop to look good and continue happening. And so there's a little bit of validity threat. It depends on how the context in which you are using those surveys. Sometimes they can be useful, but sometimes they can not really give you the right answer. So there are students, there's self-report survey, there is instructional collections. Those are like teaching portfolios. In DBER, in the field, those are very loosely described. There's not very rigorous rubrics that have been developed to measure what a good teaching portfolios look like. Other measures are course artifacts, syllabus, exam, lecture notes, assessments, other assessment pieces. Again, there are some tools to help us analyze those, but they have not been broadly used, and they are pretty time intensive. And then there's observations. Those we know can be time consuming, but they are, if you want to know what's happening in the classroom, those are the most valid measures, right? You cannot make any, there's no bias in an observation when you just go in the classroom and observe what's taking place. So we decided to focus on observation for that reason, although, again, it can be time consuming, but you can make it, if you choose the right protocol, you can make it in such a way that it's actually feasible. So when you're looking at an observation protocol, you need to consider it from different perspectives. So from an instructor, we want an observation protocol that's useful to you as an instructor so that you can learn from it, right? So we want the protocol to give you meaningful feedback. From a research perspective, I want the protocol to be aligned with what we know about best teaching practices and how people learn. And then I want enough resolution so that I can identify changes. So if I use the observation protocol to measure the impact of an initiative, I want to measure even a small change in people's practices, right? So I want a high resolution. And then in both contexts, we want the protocol to be easy to implement and to have what we call high inter-reader reliability, or an easy way to establish high inter-reader reliability. That is, if Steve watched one classroom and used the observation protocol, and I watched the same classroom and used the observation protocol, our results should match, right? And so some protocols, it's hard to establish that, and others are easier. Out there, there's two different types of protocols that exist and that have been used in our field. There's the holistic protocol, which is when you're watching the whole lecture, and at the end of the lecture, you look at the protocol and you make decisions based on what you saw during the whole lecture. And the Reform Teaching Observation Protocol, or RTOP, is an example of that. How many of you are familiar with RTOP? Okay, the next few slides will be useful. And then there's segmented protocols. Those are protocols that you use as you're observing the classroom, and usually there's a specific time frame that you have, 2 minutes, 1 minute, or 5 minutes, for example, and then you're checking during that time frame what's happening. And so that one is COPUS, and I understand that we have more familiarity with COPUS. Who's familiar with COPUS? Okay. The next slide will still be useful. Okay, good. So those are the most popular instruments that have been used in STEM in the US to measure instructional practices. This one originated in K-12, but has been used extensively in higher ed now. And this one was designed and been used exclusively in higher ed. So RTOP, the Reform Teaching Observation Protocol. So this protocol was aligned with research. So they, all the items that's contained in it align with the principle of how people learn and best teaching practices. And essentially trying to measure the extent to which the instruction provide opportunity for students to actively construct their knowledge. So it's a constructivist idea. So this is a holistic protocol, so you watch your whole class, and then you go to your paper, and then you have 25 items on a Likert scale from 0 to 4. And then you read your item, and you measure this, and you decide to what extent was this very descriptive of what I observed during this class. And then there's 3 categories: lesson design and implementation, content, and classroom culture. So what you get at the end is a score between 0 to 100. 0, that means you're very teacher-centric, so you lecture for 50 minutes with 0 participation from the class. And then student-centered is group work, where students are actively, again, constructing their knowledge. Okay. The strengths is that this protocol is grounded in the literature, so that's useful. The weaknesses is that it's very difficult to establish inter-reader reliabilities. Those categories, 0, 1, 2, 3, and 4, those Likert scale, the original designer of it actually didn't explain. It was a terrible rubric. They don't explain you what a 0 is, what a 1 is, what a 2 is. So the difference between a 2 and a 3 is left to the user's interpretation. There's a group in the geosciences who develop a more refined rubric. We tried to use that, but honestly, my research students and I, this was the most intense group meeting we ever had, and really we were almost at each other's throat debating between a 3 and a 4. And it was just, it's just a painful, and I'm on video, so it's great, a painful instrument to use. But so it's really, really hard to establish inter-reader reliability. And then the different teams that have used RTOPs, because the definition of what a 0, 1, 2, and 3, and 4 is not clear, then a score of like 50 from my group may mean something slightly different than a score of 50 in another group, because we don't have that consensus. And then when you have a change in RTOP score, it's not clear why the change happened. So let's say Steve went through one of my workshops. I measured him before the workshops, and he was an RTOP score of 40. And then after the workshop, he was an RTOP score of 50. Okay. I don't know what I mean in terms of what he changed in his instructional practice in the classroom, right? So I know it's a little bit more student-centered, but that's about all I know. COPUS, so this is the segmented one, was developed based on another protocol, the Teaching Dimension Observation Protocol, or TDOP. And so this one is a very objective measure, and it's focused on what are the students doing, what is the instructor doing. Okay, so very just behavior. And so this is how it looks. You have your minutes, so every 2-minute times point, and then you have 13 and 12 students, instructor codes, and you're just checking like what's happening during the 2-minute time points. All right, so for these first 10 minutes, it was a lecture, 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 lecture. And you guys were listening, 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 listening. Okay? That's how this works. Pretty easy to use. What you get is a percent. It's a sense of how class time was spent from the teacher and the student's perspective. Right? So you get a quantification of behavior. The strengths, it's really, really easy to use. You can have undergrads. You can train undergrads pretty easily to use these instruments. And you can achieve pretty high interpreter reliability quickly. And it gives you super high resolutions. You have 25 behaviors and percent of how class time is spent, so you can really see like even small changes. The weakness is that it's not grounded in the literature, so it's not aligned with best teaching practices. And then it's a little overwhelming to compare across 25 different behaviors, right? There's just a lot of data, especially if you want to share that with faculty so that they can reflect on their practice. It's just too overwhelming. And as a researcher, it's also not practical. So both protocols have strengths and weakness. And so my idea was that let's leverage the strengths of both of these things. So let's use the RTOP and the COPUS and apply it to the same classrooms. And let's develop kind of a new methods where we get the best of both worlds, which was the name of that paper. So let me show you how we did that. We put a camera, so this is how we collect data. This is my class at UNL. We put a camera in the back of the room and we videotape everybody. Then we go to the lab, my students Scopus everybody. And then we get this analysis. So this is the kind of output you can get from COPUS, which I think as an instructor is very cool. I get to know, so this is what we call a heat map. So this is different categories of behavior, and you get to see, you know, as your class progresses, which behavior is being represented. And so, you know, I was like presenting for a while, but I asked some questions. Maybe I had to click a question in there. So you get this cool heat map to see how you spend your class time. And then my idea was that, okay, once we have all of this COPUS data, we're going to look for this instructional style. So we're going to run a cluster analysis. And my hypothesis is that there will be different clusters that emerge, and each of these clusters which correspond to instructional styles, which means similar profile in the types of behaviors that are being represented in those classes. And then we will also RTOP every lessons, every observations, and then we will see how these RTOP scores align with these instructional styles. And if there is an alignment, then that will give some validity to these instructional styles and give some more literature grounded to this use of COPUS. So in order to do this, I needed faculty. And I'm a chemist, and I always joke with my chemist faculty, you can buy molecule, I cannot buy faculty. I cannot force faculty to do anything. And so I had to leverage different opportunities to be able to collect my data. So we got some grants at UNL to run the scientific teaching workshop series. And so participants in our workshop series were kind enough to sign up and agree to do the research part. And then I'm the evaluator on this workshop. This is a national workshop for assistant professors in chemistry. It's a 2-day boot camp in DC where they learn about pedagogies. And usually there's like, they either will start in the fall, and the workshop is in August. They either will start in the fall their position, or they have been in their position for just 1 year. So they're like brand new assistant professors. And so as part of the evaluation of the workshop, we videotaped them. So through this, we had 74 faculty who participate. We observe all of them for a week long, so not just one observation per faculty, but just a whole week. And then, so that gives you the breakdown. We've got about 100 week longs of classroom visit, which correspond to 269 individual class periods. At the time, this was one of the biggest studies of that sort. And then you have the breakdown. So all R1 institutions, and we have a distribution across the undergraduate curriculum, across class size, classroom type, so this fixed sitting like here, or more flexible environment where you can move table and desk. And then you see we have the various disciplines represented, different level of experience represented. It gives you a sense of what the variety of our population. So We use RTOP, so we use this refined rubric which actually explained differences between zeros and ones. But it was still hard, so we had 2 students at least code every videos and come to consensus after watching each videos, which is 269, so you can see how they had fun. And then this is a measure of interreliability. We did good with it, but it was painful. And then COPUS, once we had established interreliability, which was easy to establish, we just had 1 person code each videos, because that's all we needed. Okay, so then came another problem. In order to do cluster analysis, there's a statistical rule that your the number of variables that you can include in your cluster analysis depend on your sample size. So we had like 270 observations, and the rule is 2 to the n. So your sample size should be 2 to the n, with n being the number of variables. So that means that we could only have 8 of the 25 COPUS code. We could only use 8 of them. So then it came like, well, how are we going to do this? Well, it's actually not that bad. So when you do a cluster analysis, you want variability in the behaviors, right? And you want to only include behavior that are not too correlated with each other, because you're measuring the same thing, right? So there are certain behaviors that were highly correlated, and this probably doesn't come as a surprise. If the student is asking a question, you hope that the instructor is answering that question, right? And so it was a high correlation, and same thing vice versa, right? So instead of including 4 codes, you can just include 2 codes, right? So that breaks it down to 2. So we included students answering question and asking question. Then there is 3 different codes to describe group work. And we're like, well, we're not super interested in the variability at this point, and we need to reduce. So we're going to make this just group work. We don't care if it's clicker or worksheets or whatever. And then all of this behavior had very limited variability. Either they were very present across like 90% of the time of every class, or like 3% of the time. So with a cluster analysis, you want variability. And so we eliminated all of those. And some of those, like test and quiz, by default were not present because we only videotape when there was no exams taking place in the classroom. Then there was other behavior that were correlated. So asking a clicker questions. Asking a clicker question had enough variability. This follow-up on clicker question had enough variability that we included it. But instructor weighting was correlated a lot with this group work, so we eliminated that one. Lecturing and real-time writing were variable enough that we put them. Real-time writing meaning you write on the board or on the doc-cam. And then moving through class was highly correlated also with one-on-one. So we only kept moving through class. And then those ones we eliminated because they were barely there, admin and random stuff, right? So those are the 8 codes that we used to do this cluster analysis and how we decided on those 8. And this is the result. So we call it COPUS Profile 1.0. So we were able to identify 10 different COPUS profiles, so instructional styles, that we could then regroup in like 4 big categories. So there's the lecture category, which you can do it with PowerPoint or writing on the board, or you have transitional lectures, like when you have a little bit of interaction with students. Then there's the Socratic, the Q&A people with or without slides. And then the peer instruction, this is a method that you use when you use clickers, or when you have your students, you ask a clicker questions, they think about it, vote individually, and then based on the answer, if they're all over the map, you have them talk to each other and vote again. And so we had some of those, and then the more group work-oriented people. And so this is the distribution of observations. So half of the observation fell into the lecture profile type, and then about 10% in the group profile type. So just to give you a range of how this was distributed. So once we have this profile, now we can look whether or not they aligned with RTOP, which will give some like theoretical validity to them. So this is our RTOP scores data. So just to orient you, we have RTOP scores on the y-axis, and then week-long class visits on the x-axis. That means every vertical line represents 1 week of observation of one faculty. Okay? So then we color-coded it based on the profile that each of these observations fell under, and you can see a good relationships, right? Higher RTOP scores fell into the group profiles, right? And then the lecture side fell more into the lower RTOP scores. So that was a sense that, okay, we have like, this provides some validity to these COPUS profile methods. In other words, it also highlights how RTOP is not very descriptive, right? Because you can have a score of 40, be doing lecture, but be doing also group work. right? So understanding what a score of 40 means is challenging. One other thing that was interesting from looking at this data is like if you zoom in on 1 week of instructional practices for a couple of different faculty, you'll notice something interesting. So this particular faculty, they taught through a lecture for all 3 days, so very consistent. But then this faculty talked with lecture for 2 days, and then had some Socratic lecturing. And then this other faculty had like everything from lecture to peer instruction to group work, right? And so our strategy to go visit faculty at least for a whole week was necessary, because we can see that there's a variety of practices that they are using within the same week. So if I would have only gone on that day, I would have misrepresented this particular faculty's instructional practice. Okay, so we have like, by looking at our profiles and RTOP, we kind of theoretically validated that these profile methods work. And then some people at UBC, University of British Columbia, they saw one of our talk and they were like, oh, let's try it in biology. And they were interested to see if the profile were linked to better students' learning. So they implemented concept inventory at the beginning of bio. I think it was general bio at the beginning of general bio, and then at the end, and then they COPUSed all the lectures, and then they look if there was any relationship. And they found that those COPUS profiles that are more on the student-centered side resulted in more learning on the student side, the higher score on the concept inventory, right? So that further like kind of validate the methods. So we were very excited about this. We're like, well, we're able to say that there's only 10 instructional style that STEM faculty use. But then upon reflection, it was also, the sample that we had was problematic. The data came from either very young chemistry faculty at our one institution, and the other part was coming from UNL, which had adopted clickers. So we were like, wow, there's a lot of clicker type profiles. And we know from talking to people that not everybody uses clickers, and that there's other ways to have students talk to each other. So we thought that the sample was not great. So we wanted to test the generalizability of those profiles. So we called some friends. We sent on our Deberly served an email and saying, hey, if you have COPUS data that you collected for other reasons, would you mind sharing it with us? And we will try to do the similar analysis and see if our COPUS profile are generalizable. So this is the people that came and played with us and shared their anonymized data. And so that really greatly enhanced our sample size and the diversity of our sample size. So now we have over 2,000 class and over 500 faculty being represented compared to like 71. Again, it's not perfect because it was like a secondary use of data, so it was not like by design. So there's a little bit overrepresentation of biologists and chemists, and then freshman level courses. But this is still like by far the largest study to date of that nature. And another caveat is that it's mostly doctor granting, again, research intensive institution, right? So we still need to do more work in understanding how primary undergraduate institutions work. And that's just extra data. We observed them again for more than one class. Okay, so this is COPUS Profile 2.0. So now we didn't have 10, we had 7. And rather than walking you through each of them, we put them in 3 different categories and kind of like summarize what those big, broader instructional styles represent. So we have the didactic group. That's about 55% of the sample, so similar to what we had found before. And this is where you can see that for, on average, about 80% of class time is spent lecturing. Okay? And the students are not doing a lot of group work. They're asking some questions, but it's mostly lecturing. Then you go to the second big group. We call it interactive lecturing. That was about a quarter of our sample. And now you see that lecture has decreased quite drastically. And now we see some group work happening either through clicker question or other means, right? And then we have our student-centered, so those 3 clusters that together represent about 20% of the data. And then you see, once again, a big decrease in lecture. Now it's about, on average, about half of the time only is spent on lecture. And then we see more students doing group work again. Like now we have worksheets showing up. Okay? So those are like the 3 big instructional styles that we observe. We can classify it in each of these 7, but I think for broader thinking, it's useful to just stick with those 3. And so since I've been lecturing at you for like too long, we're going to do an activity now to help you wake you up, right? Because it's late on Friday. And then I think I'm going to do a predict, and then you're going to observe. We don't have too much explanations because it's people's behavior, and unless we talk to them, we don't know why they're behaving that way. But we're going to do a predict and observe, and hopefully that will help you remember those results a bit more. So we have these 3 instructional styles. How do you think they vary by different classroom layout? So if you have an amphitheater like this versus a place when you have those small desks, you know, that you can move around, or like round table, which of these styles do you think will be most represented in which environment? Classroom size, 200 versus 10. Which style do you think will be represented more? Science discipline, and then we can do a battle of the disciplines, right? Do the chemists, the maths, the biologists win, and why would we win? And then throughout the undergraduate curriculum, freshmen, sophomore, etc. So I want you to pair up, talk to your neighbors, or triple up. And if you're alone, you have to come down and talk to your neighbors. And then make those predictions. So what do you think is going to happen? Which style will be represented in which context? And I give you like 2 minutes to do this, or so. You all have made your predictions. I do not have prizes if your predictions works, but you'll get a satisfaction of knowing you have the right answer. All right. So I'm going to break each of these 4. So I believe, if I did this right. OK, so this is the color coding. Student-centered green, interactive lecture yellow, and didactic red. So this is course level. And I'll let you digest. Is this surprising? Right? Why is that surprising? What did you expect and why? You expected more green and higher level, right? Yeah. I was really surprised by this, honestly. Yeah?
But that does not account for different disciplines, right?
Not yet.
Everybody in the same boat.
Yeah, yeah.
Okay.
It's all the disciplines together, yeah. But I expected, so from, again, a US perspective, a lot of the money that has been spent by the National Science Foundation is on revamping and improving the first 2 years of STEM courses, right? So you would think, and especially where we collected those data, it's places where things are happening, we're trying to change. So I was really surprised by this. I thought there would be more green here, actually, because more money has been spent for this to improve those environments. And also, there's a tendency to think that at a higher level, students are more engaged with the content and variety of methods, but that's not what we saw. OK, class size. Does that match your predictions? Yeah, small size is easier to do student-centered than large classes. So the flip side of this is that, wow, you can actually do active learning in large classes. That's a barrier I hear often from faculty. Well, in this environment, what do you expect me to do? There's no way we can do group work. Well, some people have figured out how to make this work. So maybe it's not so much the physical constraints, it's just creatively we have to think about how we can use the space, but it is possible to do active learning. The other flip side is like, yes, the smaller environment, you have more active learning, but still almost half of the observation in those environments are didactic, right? And so there's pros and cons in each of these data points, right? OK, classroom layout. Right, so a place where you have small round table or small desks that you can move around, you get more active learning going on or student-centered strategies, and more lecture-centric in a fixed setting. But again, still, even in flexible environment, we are close to 50% of lecture focus environment.
How much of that is actually tied to class size, though? Because you're not going to have
yeah, we look at the
600 students
yeah.
and 3 tables and chairs.
Right. No, well, actually, they do exist, but there are places where in Arizona they have this huge room where they have round tables of like 5 to 6 students per table or something like that. And they fit like 300-400 students. It's called the scale-up classrooms, and people do it with like 400 or 500. But yeah, there's a little bit of a relationship there. One thing I like to identify with those data is that there's a big push on campuses to create active learning classrooms, right? And with the assumption that if you have an active learning classroom, active learning is going to be used in that classroom. And I think this data kind of indicate that, well, maybe this one, maybe not, right? It's a very different environment, and people have to be trained on using those environments. And so the amount of money you spent on the infrastructure, you should probably spend as much money on training people to use these environments, yeah?
Yeah, and maybe the student center might be overrepresented because people who do student-centered learning are going to request those rooms.
Yeah, fair enough, yes, yes. Okay, and the last one, that's the most fun one. It's organized from most didactic to least didactic. So if you're a math person, you tap yourself in the back. Good job, math people. And if you're chemistry, you go hide under the desk and pretend that you don't exist. So I will do that. It is interesting, right? So there are disciplinary differences. But for the most part, I think what this slide tells you, if you look at all the data points, right, is that didactic still dominates, right? So that's the picture that this data is painting at this point. One other interesting finding that relates to something I mentioned earlier when we were looking at the RTOP data, we wanted to see whether or not we could replicate that results that instructors have a variety of instructional style. So I think there's an assumption sometimes from professional development facilitators like me that faculty always teach the same way, right? You have that one thing that you do and you always do it the same way. And so the RTOP data indicated that potentially not, and this data also indicated that not. The more observation we were doing, the more different styles we were starting to observe, which is an indication that faculty use a variety of styles. They don't just lecture all the time, they don't just do group work all the time. And I think that's very valuable to know that for various reasons. Once, when you evaluate faculty, at least at my institution, in my department, I get my senior faculty who come and observe me once a semester. And then they write their letter and identify if I'm a good teacher or a bad teacher. So if you come on a day where, you know, I think the best strategy to teach this content is lecturing, and if you think I should be doing active learning, you're going to judge me poorly. But if you come on another day and I'm doing active learning, and you're a faculty who think like, this looks very chaotic, what in the world can the students be learning in that environment, right? I'm going to get downgraded too, right? And so you have to have like multiple observation points. You can't just have one observation point when you're doing evaluation of instructional faculty. Yes. So I think I'm okay on time. The take-home message. So and again, this is the larger study that we have today. So if we are trying to measure impact of all these initiatives, we can say that it has limited impact. We see a lot of didactic practices. Flexible classroom layout and small courses size do not necessarily lead to more active learning or student-centered practices. And then you have to go and observe people more than once if you want to really understand what their instructional style is. There is still a caveat with this sample. Again, we mostly focus on research-intensive institutions. One problems with COPUS, it's very objective, measure behavior, doesn't measure the quality of the content being taught, right? And so we would need another observation protocol to do that. And then that was mentioned in some of the conversation, only what's happening in the lecture hall is being characterized. And so faculty engage students in many different ways outside the lecture hall, right? So this is only limited to what's happening inside the classroom. There's other things that faculty could be doing outside that's not taking into account, like the lab or the RESI. Okay, so the implications that we made in the science paper was that we have to change how we, at least in the US, how we're rewarding teaching at a research-intensive institutions. If we start to shift, or at least put more value on teaching, then we'll be able to create more opportunities for people to have time and resources to improve their instructional practices. We need to train faculty better with teaching. You know, we all went through a PhD program where we focused on becoming a researcher, and then you know, my husband was like that. He's an organic chemist, and then he went from his PhD postdoc, barely taught because he had a fellowship, And then the first day at Nebraska, it's like, congratulations, you're teaching organic chemistry. Here are your 200 students and a textbook go. You know, and that happens a lot, right? So we need to really improve our pedagogical training for grad students and then for the current faculty members. And then this is a question that I'm very interested in, is how do you measure teaching? And I truly believe that one instrument is not enough. So we know students' evaluation are clearly not enough. I think classroom observation are useful, but not enough. I think we need to think more of a package and triangulating data from different sources. But we have yet to kind of make this work and identify a good way to look at all of this data and make a decision about one's instructional practice and ways to improve it. If you like COPUS, we have an app for it. My postdoc, I had designed a very, very like poor man's person app before he came. This guy is an R guru, and so he was able to make my app much, much better. And so now you can, we give you a template, an Excel template, where you can enter your COPUS data, and then the app will do all the analysis for you, give you like cute little graphs like this, where you can choose like which behaviors you want to be plotted. So you can see how you're spending your class time, it calculates average percentages and all of that. You can have more than one observations. If you want to use this for research, you can do inter-rater reliability. It's in its beta form, so if you use it and there's bugs, please let us know so we can fix them. So this is done with Jordan Harshman. He was my postdoc, now is out of Auburn. And so this work was done with a lot of people. And so the first paper was mostly my postdoc grad students and undergraduate students who spent hours watching videos. And then the science paper was just a huge collaborations between people all over North America, really. And they all had received money from various places in order to do this data collection. So we have to thank all of these people for funding parts of this project. And with that, that's all I have. So I can take any questions. Yes?
So you mentioned at the beginning that a lot of STEM students who start off decide to leave.
Mm-hmm.
Is there literature similar to what you've been working on to show what non-STEM faculty are doing for strategies?
Yeah, we were just running into that a couple of weeks ago. So we looked for that literature, and the rate is actually interestingly similar. I think it's like 40% or something, 40, 50. So if you look at the STEM, it's 40, 50 of the students who leave STEM. But if you look at humanities, it's also a similar rate, actually. And so there's the argument that we've been making from a National Science Foundation perspective, I think we're going to have to refine it a little bit. So students are just shifting a lot. The problem is when you're looking at students who really wanted to do STEM, and then they're saying like, what I experienced in those courses was so terrible that now I don't want to do it. There's going to be some shift because of interest and realizing chemistry is not for me, you know, that's not what I thought it was going to be. But for the students who really wanted to do it, and then where whatever environment they experience become a barrier, that's the problem. And even the Seymour paper will say, found out that even for the students who are in STEM, they complain about the instructional practices and how hurdle it is to their learning. Mm-hmm.
Do you have any idea on sort of the resources that have been available? So people who have adopted active learning practices, say with the class of 200 or class of 300, mm-hmm. have they tended to have been part of a study where there's funding to actually make this happen or flip their classroom? Or is it mostly just individuals kind of on their own deciding, yeah, I'm going to do this and altering the practices?
I don't have the data to answer that question. From my own data, I would say it's probably a mix. There's those, we're talking early adopter people who are like, they're innovative and they want to learn and implement new things. And so they don't go through training, they just learn on their own and implement things in their classroom. But there are also people who go through pedagogical training and then implement. I think it's a mix, but I don't have a firm answer based, based on data.
Is there any data or any statistical mechanism that you can use to correlate the different profiles that you get from the RTOP or the COPUS with student success?
So that's what the University of British Columbia people tried to do. They did this concept inventory pre-post and measure learning gains and look at the correlation between learning gains and the type of profile in student-centered learning that was happening, and they found the correlations. But that's the only study and that was a poster. And so we have not done that piece, and I don't know of anybody but them who have done that. But I think that would be a logical next step.
I mean, is that statistically hard to do, or is it just...
No, it's just logistically hard to do, right? Because we don't have a lot of good assessment tools. So in bio, you guys are lucky, you have a lot of assessment tools. But like a good assessment tool that measure conceptual understanding, and having an instructor agree to do like pre-post on students, having a good response rate from your students, plus having an instructor that allows you to visit, observe the class. It just logistically is challenging. That's the big hurdle. But we often get the question like, how much active learning is the magical number, right? Is it 50% of class time, 60% class time?
Yeah.
Does there seem to be any, what's your sense in terms of how much institutional buy-in there is? This is one thing, there's this big push to improve how we teach and whatnot, but there isn't the time given to actually develop it, because as you said, you dropped into the classroom with no training, and somebody has to has a high teaching load or a high teaching load and research, and there's just not that time to truly think, stop, develop. Does there seem to be any kind of a movement at all within institutions?
So that's why we wrote that in the science paper, because we figured it was like a policy forum, whatever, so people may be more inclined to look at that. So we made that explicit, like institutions need to shift their focus and provide more resources for teaching so people can improve their teaching. I think overall, yeah, I think the Association of American Universities is pretty high profile in the US, and they have these huge STEM initiatives. And so all those universities who are part of this organization, they are compelled through peer pressure to kind of pay attention more to teaching. So I think as more of this kind of research pops up, there's conversations happening that may not be that were not happening like 10 years ago. And so hopefully we see a shift, but it's academia, right? So it's not going to happen tomorrow. It's going to be a slow process, but I think the right conversations are happening. And, there's hope, yes.
Last chance for a question? If not, I'd like to thank Marilyne for coming.